Let's look at modules over polynomial rings. We've already looked at one example of modules over the ring of integers, and there we showed it's just nothing but the set of abelian groups. Those are exactly the modules. Now let's look at polynomial rings now. So what is a polynomial ring? What do we have in mind? So example, so let's take a field K, and so let K be a field, and the ring that we will consider is the ring of polynomials in one variable x with coefficients in the field K. Okay. So of course you've seen this ring before, looked at various properties of it, ideals and so on and so forth. Now let's try and understand what modules over this ring will look like. Okay, so let me give you examples of modules first. So let V be a K vector space. So let it be a vector space over the field K. So it's the first piece of data I'll start with, and I also need another piece of information, which is a linear transformation on V. Okay, let T from V to V be a linear operator or a linear transformation. Okay, recall linear operator from linear algebra is just a map from V to V which satisfies the following properties. If I take T of x plus y, that's Tx plus Ty, and if I sort of scalar multiply, then T of alpha x is just alpha Tx. Okay, and this is now of course for all alpha coming from the field K, for all x's and y's coming from the vector space V. Okay, so this is a linear operator. Now, if I take a vector space and a linear operator on that vector space, this data here can be used to define a module over the ring R. Okay, how is that? So let me describe this construction. We can use this pair of information V comma T to define an R module structure on the same space V, in fact. Okay, I can make V into an R module or a left R module as follows. So when I say R module, usually without qualifying it, I usually always mean left R module. Okay, so when I say this, I always mean left R module. And note, we have already said that left and right coincide if the ring is commutative, which in this case it is in fact commutative here. Okay, we can use this to define an R module structure on V. So let me describe the R module structure as follows. Okay, so what do we need to define an R module structure? Well, recall V is already an abelian group, so there is nothing further to do there. I already have an addition on V. What I need to define is really the scalar multiplication, right? So I need to tell you, define the scalar multiplication map Kx cross V to V, which satisfies those four axioms. Okay, so let's define it as follows. What are elements of Kx first? So I need to tell you what a typical element of Kx looks like. So let me take an element of Kx. So what's a element of Kx? It's a polynomial. So here's a typical element of Kx. So I need to define scalar multiplication by elements of the ring R. Okay, now the scalars are not just elements of the field K alone. The scalars are actually polynomials in the variable x. Okay, so this guy is now a scalar really, because I'm allowing scalars to come from my ring R. Okay, so I should take this scalar and I should take some vector. So okay, let me not use x for vectors anymore. So maybe even in the previous, going back here, since I already have an x there, so maybe it's safer to call this variable x as something else so that there is no confusion with the other x. So let me just say let's use v1 and v2 here for my vectors. So let me say t of v1 plus v2 is t v1 plus t v2, t of alpha v is alpha t of v. Okay, and this is for all v1, v2 in my vector space v. Okay, that was just in the definition of the linear transformation. So now I let me come back to my main object, which is to try and define a scalar multiplication. So take this polynomial, which is a element of my ring R. I should tell you how to scalar multiply it with a vector v, right? Now the definition is as follows. We just try to do the most intuitive thing. So let's define it as, so let me look at the constant term. Alpha naught is a constant term of the polynomial. The constant term, remember, is an element of k. Okay, all the coefficients in fact are elements of k. So I'll take this element alpha naught of k, and after all, v is a k vector space, right? I already know how to do scalar multiplication there. So v is a vector in my vector space, alpha naught is a scalar from k. So I already know how to multiply elements of k with elements of v. So this is just the usual scalar multiplication in my vector space v, multiplication by scalars coming from k, by scalars in k. So this is already given, right? I know that v, I started with a k vector space v. So this alpha naught v is just the usual scalar multiplication of v with alpha naught. Now the trouble comes in the next term. I have alpha 1 x, right? Now I need to somehow figure out a way of defining how this element acts on v. Now if I have just alpha 1, of course alpha 1 into v is just the usual scalar multiplication, but I don't know what to do with the x here. Okay, so that's really what this additional linear operator t is useful for. So here's our definition. The second term, alpha 1 x, we make it act on v as follows. X sort of acts like the operator t. Okay, so tv now is again some vector in v. Alpha 1 is a scalar in k. So scalar in k times vector in v, I know how to do it because that's the scalar multiplication in the vector space v. Okay, plus let's look at the next term, x square, right? This is now going to look like alpha 2 x square. So I will define it as follows. This is just t square acting on v. Okay, now what is t square? So recall, t square is just shorthand notation for t composed with t. In other words, t square v is just the vector t acting on tv. Okay, plus dot 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 alpha n. This is now t power n acting on v. Again, t power n just means the repeated composition of t n times. Okay, so this is my definition. I make my definition in this manner. So I say that my scalar, this polynomial alpha naught plus alpha 1 plus blah 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 acting on v gives me this answer, alpha naught v plus alpha 1 tv plus alpha 2 t square v and so on. Okay, now we have to check that this satisfies all the axioms. Okay, once we check that, then of course it's a well defined module. So let's check the axioms. That's our task now. So let's check the axioms. Okay, so what's the first axiom say? It says that if I take a scalar, so in my case my scalar is some polynomial in x, so I'll just call it p of x for now, times v1 plus v2, that should give me this polynomial acting on v1 plus this polynomial acting on v2. Okay, where so p of x I'm just using as, so this is my polynomial alpha naught plus alpha 1 x plus dot dot dot. Okay, and of course all the elements come from the appropriate spaces, v1 and v2 come from v, the alphas are all elements of k. Okay, so I have to check if this is true. So is this true is the question, right, according to my definition. Just a question of writing out both sides. So observe that so the formula that I wrote out, so what is the left hand side, therefore this is just going to be alpha naught plus, okay, so let me write it as this, alpha naught times v1 plus v2 plus alpha 1 t acting on v1 plus v2 plus alpha 2 t square acting on v1 plus v2 and so on, okay, till I reach the nth term. But the key observation here is that each of these terms actually splits into two pieces. Okay, so t of v1 plus v2, remember t was a linear operator, so I can write it as t v1 plus t v2. If t is a linear operator, t composition t is also a linear operator, so t square is linear. So t square of v1 plus v2 will again split into two pieces. So alpha naught multiplied by v1 plus v2 is alpha naught v1 plus alpha naught v2, because you have distributivity in the vector space V. So I sort of split this into two pieces. I just write all the v1s first, t v1 plus alpha 2 t square v1, etc., etc. And then below it I write all the v2 terms, alpha naught v2 plus alpha 1 t v2 plus alpha 2 t square v2 and so on. Okay, and observe that's exactly the right hand side, okay, where you have to sort of do it in two separate steps. Okay, so that's the first axiom. Now the second axiom is sort of similar. It's in fact even easier. The second axiom just uses the fact that this is linear, so I will just leave the second axiom for you to check. It's an exercise. The third axiom, which is that if I multiply two scalars, okay, in other words, I take two polynomials p of x and q of x and I multiply them in my ring R and then act on a vector v, then the answer should be the same as the answer I get when I first take px, act it on the answer that I get when I act qx on v. Okay, so this is what I need to check again. I need to see if this statement is true for my third axiom. And again, let's write both sides out. So what is p into q? So now this involves multiplication in my ring of polynomials. So remember, alpha 1x plus alpha 2x squared blah 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 till some finite point. Qx looks like beta 0 plus beta 1x plus beta 2x square and so on. Now their product px times qx is computed as follows, right? So what's the constant term? It's alpha naught beta naught. The coefficient of x is alpha naught beta 1 plus alpha 1 beta naught and so on. So you sort of know what to do. Beta 2 alpha 1 beta 1 alpha 2 beta naught x square and so on, right? So this is how we compute the product of p and q. And so now when we act the product pq on a vector v, what does it give us? Well, we just have to do the following. Wherever you see, so each of these numbers, so I write alpha naught beta naught, multiply it by the scalar v, the scalar alpha naught beta naught times v plus the scalar alpha naught beta 1 plus alpha 1 beta naught times, so remember this term x means I should replace it with tv, the next term with t square v and so on. So that's my that's how px qx acts. Now let's compute the right hand side, which is px acting on qx acting on v. So what does that mean? I first have to figure out what qx acting on v is, what this vector is. Well, this vector by definition is beta naught v plus tv and so on. So it's just a question of writing this out, etc. And now I try to act px on this vector qxv. Right. So how does px act on this vector? Well, it is alpha naught times this whole vector. So I plug this whole vector in here, okay, plus alpha, let's write that down here, alpha 1 t acting on, well, that same vector, this vector, plus alpha 2 t square acting on the very same vector and so on, right, dot dot dot. So that's my right hand side. Px acting on qx of v is just alpha naught of this whole thing plus alpha 1 t acting on that whole thing plus alpha 2 t square acting on that whole thing and so on. Okay, now we can sort of so let's take one representative term and see what's going on, and that will sort of tell us what to do in general. So now observe, for example, if I take a typical term, so what does a typical term look like? So typical term in this summation looks like, so let me take the kth term. It looks like alpha k t power k acting on that vector in the inside, which is beta 1 beta naught plus beta 1 t v plus beta 2 t square v and so on. Now when I act at t power k on a combination of vectors, which each of which is t v, t square v, t cube v and so on, I just have to make the following observation that let's write this here, t power k on some vector which looks like t power j acting on v, it's like I have already composed t with itself j times, and I further need to compose it with itself k times, so it's t to the k plus j acting on v. So this is the key observation here, that t to the k acting on t to the jv is t to the k plus jv. Okay, so this guy here will just become alpha k beta naught t to the kv plus alpha k beta 1 t to the k plus 1 v and so on. Okay, so that will become the whole expansion. Okay, now I've just written out the general term there. Now you can sort of see what goes on. If you just go back and plug it in, you will observe the following, that px acting on qx acting on v is in fact nothing but the sum over all k is alpha k. So it's a double sum now. K runs over all the possibilities, k 0 to whatever the degree of p is, whatever the top limit is. Beta j again runs from 0 to the degree of q. So let me say to the degree of p. This runs to the degree of the polynomial q. Alpha k beta j, and what do I get here? T to the k plus j acting on v. Okay, so I've just said the typical term, the kth term, I've sort of shown you what it looks like. It looks like this. But then to do the entire sum, I need to also allow k to vary from 0, 1, 2, 3 and so on. So I'm just doing the whole thing in one go. So that's my answer. Okay, but observe, that's exactly what we got when we took the product of alpha of p and q. So observe, what is this answer here, px qx on v. The typical term here is exactly alpha k beta j, and the power of t in front is k plus j. Okay, so observe, this is nothing but this looks like the sum alpha, let's say alpha I beta j. So what does a typical term look like? This is the coefficient. So I should say px so let's write this out also as a summation. So this looks like, if I want to know what is the coefficient of some t to the let's call this k, maybe kj. If I want to know what is the coefficient of t to the iv, then this is the sum over all k and j such that k plus j equals I. Okay, and this is now a sum I going from 0 to whatever the degree of pq is. Okay, now so I'll just leave it for you to nail down the final details. So observe this final term here that I have, which I get when I take the product, is actually the same as the term I get here. Okay, so those two answers are actually the same. So this is the same as the left hand side that I obtained earlier. Okay, so that was slightly lengthy but completely elementary. It's just from the definition itself. And let me check the final axiom, axiom 4, which says that if I take the identity element of my ring and I scalar multiply it with any vector, I should get back that vector. But observe, the identity element of the ring here is nothing but, well, what is the identity element? It's just this polynomial, right? I should think of it as this polynomial. 1 is the constant term plus 0x plus 0x square and so on acting on v, and that by definition is just 1 acting on v. This is the usual scalar multiplication, and then the rest of the terms don't contribute because I get zeros in front. Okay, so this is now just the usual scalar multiplication. So this one is in k, this is an element of v, and this is scalar multiplication in the vector space V, and there of course we know the answer is V. Okay, this is by the axioms of the vector space. So what I get is that 1 dot V is exactly V by the fact that V is a vector space over K. Okay. So what have we managed to do? We have managed to show that all the 4 axioms hold in this case. Okay. So we have therefore shown the following. So conclusion: is the following. If I give you a pair of a vector space over K together with a linear operator on that vector space, okay, V is a vector space over a field K and T is a linear operator on that vector space, then this pair gives me the structure. This allows me to defines a Kx module structure on my vector space V. Okay. And in fact the converse is also true, that if I am given a Kx module, then from that I can extract a vector space and a linear operator. Okay. So let me quickly tell you what the converse is. So suppose I am given a Kx module. Conversely, if V is a Kx module, maybe we will call it M, let us call this M. Suppose M is a Kx module, then from this M I can extract a vector space and a linear operator as follows. If M is a Kx module, observe that the constants, so I can define a vector space as follows. So let us define a vector space V as follows. I will take V to just be the set M itself with scalar multiplication as follows, with scalar multiplication by elements of K, right. I have to make it a K vector space. I can do this. So if M is a Kx module, we can obtain such a pair V comma T as follows. So that's what I am trying to do, construct a vector space and a linear operator on it. The vector space is just the same as the space M itself, but now I want to think of it, I need to tell you how to do scalar multiplication by elements of K. Well, you just say the following. Say I want to take an element V in M and I want to figure out how to scalar multiply it with a scalar coming from K, right. How should we define this is the question, and the answer is, well, a scalar is just a constant polynomial, right. I can think of the scalar, for example, as just this, think of it as constant is alpha, constant term is alpha, and all the other coefficients are zeros. So a scalar is a particular example of a polynomial, just a constant polynomial. So take that constant polynomial and you act on V. Okay. And what do you mean by act on B? I am after all given that M is a Kx module, right. So I am given an action of Kx on M. In particular, I am given an action of all the constant polynomials. So that's all I am saying. Define the action of the scalar alpha on V as just the action of the constant polynomial alpha on V. Okay. So that's my definition. And my linear operator T from V to V is obtained as follows. Define the linear operator T by saying T acting on V is just the action of X on V. Okay. So X, remember, is again a polynomial. It's a very special polynomial, the degree 1 homogeneous polynomial, X power 1. I just look at how X acts on V. Okay. That again is given because V is after all given to be a Kx module. M is given to be a Kx module. So I just use the given action. So TV is defined like this, xv. Okay, so this is for all v in V. So x is my special polynomial here. Okay, so given a Kx module, I can get these two pieces of information. One, I can define a vector space over K, which is the same underlying set M, but in which the scalar multiplication is just the same as the action by the constant polynomials. And I can get a linear operator from this action t. I can get a linear operator t from this action as follows. I just take the action of the special polynomial x on this module. Okay, and what you now have to check, which I leave as an exercise. So exercise, check that V is in fact a k vector space and T is in fact a linear operator, and moreover the action of any polynomial px is sort of given by the same prescription as before, is given as before, meaning this polynomial px acting on V will just be alpha naught V plus alpha 1 TV plus alpha n t power n. Okay, in other words, if you started with this pair, so on the one hand I took M, and from M I have constructed a pair V comma T, right. Now we have already described a way of starting with a pair Vt and constructing a module from it. Okay. Now what we are saying is that these two are really inverse processes of each other. Okay. If I am already given a module to start with, I extract the V and the T from it. Now having gotten this pair, I can construct a module out of that by our previous formula, but doing that just gives me back the same module n. Okay. So again, this is like our previous principle that abelian groups and Z modules are the same thing. Similarly here, the principle, the final conclusion is the following slightly loosely stated fact, that Kx modules are the same as pairs V comma T. Okay, and where V is a k vector space and T is a linear operator on K. Okay, so these two things are the same. So of course the study on the right hand side is of a linear operator on a vector space is really the key thing one does in linear algebra, right. So this is really, this belongs in linear algebra, and in some sense many theorems from linear algebra can be fruitfully obtained or studied from the point of view of modules. Okay, if you study modules over rings, in particular module over the ring Kx, what you actually get as a corollary is some nice facts about linear operators acting on vector spaces. Okay.